Well, hello, thanks for clicking on the talk. I want to start by thanking the session organizers for the opportunity to participate. What I'm presenting is a paper that's under review that is a product of a new Ameriflux Network working group on natural climate solutions. So what I'll share largely represents the perspective of my diverse and talented co-author team. Some of this is also a natural extension of work published earlier this year by Kyle Mohammed, thinking about flux towers as a tool for assessing natural climate solutions. So please check out Kyle's paper when you get a chance. All right, in many respects, the rationale for this work sort of falls under the category of old news, right? We've known for a long time that terrestrial ecosystems are a really important but highly variable sink for anthropogenic emissions of CO2. On the other hand, historically, it's been difficult to predict the future fate of the land carbon sink, with models disagreeing on its magnitude and even direction by the end of this century. That the models have such a hard time with this problem is not particularly surprising because this is an incredibly complex system, integrating processes occurring over scales as small as subcellular in the case of photosynthesis, up to entire plants and ecosystems and landscapes with a lot of interactions and climate feedbacks baked in. But undaunted by the complexity, collectively, we have invested huge amounts of material resources and time to developing tools for measuring, understanding, and predicting land carbon uptake. All right, so a prime example has been the evolution over the past 20 years or so of flux tower networks, which aggregate, standardize, and redistribute continuous time series on ecosystem scale exchanges of carbon, water, energy, and other greenhouse gases between the land surface and the atmosphere. We've also invested in big, grand global climate change experiments and a growing set of remote sensing platforms capable of detecting not only features of canopy structure, but also function, and models that are ever growing in terms of their process richness, and also in new strategies for teaching early career scientists how to work effectively across these disparate tool sets. Now, as the impacts of climate change are becoming more sensible, right, and the need to mitigate the problem ever the more clear, there is momentum growing surrounding the idea that we can manage our ecosystems in a way that enhances their ability to suck CO2 out of the atmosphere, or that reduces ecosystem emissions of other greenhouse gases. These are so-called natural or nature-based climate solutions, and I'm going to use those terms interchangeably from this point forward. What you see here is an incomplete list of viable natural climate solution strategies for the United States, with reforestation really coming out on top in terms of overall expected mitigation potential. But when carbon prices are low, some of the ag-based strategies really appear to be relatively low-hanging fruit. We have to recognize that these are not a panacea for climate change. The only way to stop climate change is with rapid and economy-wide decarbonization. Okay? But provided that is happening, natural climate solutions are parts of most pathways to net zero, and because a lot of them look like restoration, they have some really important co-benefits, for example, for soil health, air and water quality, and biodiversity. The support for natural climate solutions comes from some really, let's say, unexpected places. It's an unusual coalition including both very conservative and liberal lawmakers, the private sector, which is excited about the fact that most of these strategies are right now being implemented through private carbon markets, from conservation groups that get excited about the co-benefits, and from farmers and forest managers and the industries that represent them. Despite this enthusiasm, there remains a substantial amount of uncertainty surrounding not only the mitigation potential of natural climate solutions, but also the extent to which these managed alterations to carbon cycling will affect the closely coupled water and energy cycles at local scales. Right? So we'll call these biophysical impacts. The outline for the rest of the talk is to discuss some of the sources of this uncertainty and also to propose some paths forward for confronting it that critically leverage pre-existing investments in terrestrial carbon cycle research. So one reason why so much uncertainty exists is that historically, when thinking about natural climate solutions, we've really focused on just a small piece of the carbon cycle puzzle. So in agricultural systems, the primary variable of interest has been soil carbon, which can be measured by physically extracting soils and analyzing them in the lab. And in forests, we've been really focused on carbon stored in above ground tree biomass, which is estimated from empirical allometric relationships forced by measurements of tree diameter and sometimes tree height. These measurements are really easy and cheap to make, which is a really good thing, but this approach has some real downsides. We can, for example, be missing in our accounting really important carbon stocks within the ecosystem. Alone, these data are insufficient to inform our understanding of the processes that might govern a change in soil carbon. It can be difficult to design sampling strategies that can properly capture heterogeneity in soil carbon or tree biomass across the landscape. And importantly, it takes a really long time, many years, for a signal to emerge from the noise with these data, such that we might have to wait 5 years to understand if the projected, let's say, carbon benefits of a natural climate solutions project were even in the right ballpark. All right, and that's certainly a problem. So to summarize, there are big mismatches in scale between the plot level scales where these data are collected, the ecosystem and landscape scales where projects are implemented, and the regional scales where policy decisions are made. And to some extent, satellite data can be used to help us cross and bridge these scales, but the output will only be as good as the input. And for many categories of natural climate solutions, the input data, right, observations on demonstrated effects, are relatively sparse, such that we do not yet have spatially explicit maps of the mitigation potential of many natural climate solution strategies. We do not yet know where in the Corn Belt cover cropping is likely to most succeed as a climate mitigation tool. The maps that do exist tend to be focused on forested strategies, but again, informed only by information on above ground biomass. Getting back to this idea of biophysical impacts, here's a paper that came out about the same time I was starting graduate school, which showed that particularly in arid parts of the world, strategies like afforestation designed to enhance carbon sequestration had really negative effects on local hydrology, which posed big problems for water resource management. So clearly this is an example of an undesirable biophysical impact. On the other hand, sometimes the biophysical impacts can be favorable from a climatic perspective. So for the last 5 years, my lab group has been working to understand the potential links between a century of reforestation in the eastern United States and an associated and suspicious absence of warming across the region that's sometimes called the southeastern US warming hole. And using a variety of approaches, including synthesis of nearly 60 flux towers in the region, we've shown that relative to grasslands and croplands, forests tend to have not only cooler land surface temperature, but also cooler near surface air temperature, looking at it a few different ways. So here's an example of a natural climate solution, reforestation in the eastern United States, which appears to confer a climate adaptation benefit with respect to temperature, in addition to a carbon mitigation benefit. One more problem, and it's a big one, concerns the permanence or durability of carbon stored in ecosystems. So looking forward, we know that droughts and drought-driven mortality are going to become more frequent and intense, that insect outbreaks will become increasingly devastating, and that we should expect more wildfire. And it is critical to point out that the carbon market accounting protocols right now do not consider explicitly the potential for these climate feedbacks in any way. So that seems like enough problems. Why don't we address some solutions, or at least pass forward for confronting this uncertainty? What you see here is an illustration of the result of those decades of investments in tools for understanding, measuring, and predicting the land carbon sink. The important point here is that with the exception of what appears in the lower left-hand corner here, and perhaps some remote sensing data, the vast majority of these tools are not being used explicitly to constrain uncertainty surrounding natural climate solutions. And it's particularly striking that flux towers and flux tower networks are not yet being used for this purpose, because again, this is our only source of information on ecosystem scale exchanges of CO2 between the land surface and the atmosphere, which incidentally will respond very quickly to changes in land cover management. So there's huge opportunity to leverage the hundreds of flux tower sites contained in Ameriflux, many of which are now adopting a completely open data use policy. Within the network, there are also a fair number of paired sites where we'll have ecosystems that experience different management treatments, but the same macroclimate. And these can be really useful for giving a holistic perspective on the impacts of natural climate solution strategies. So for an example, let's consider a set of 3 towers co-located in the Duke Forest over a successional chronosequence, moving from an old grass field to a pine plantation to a hardwood forest. These towers ran from 2001 to 2008. And the numbers here on the right show that as we move along the successional trajectory, as reforestation proceeds, there is a big benefit for carbon uptake. There's also a clear reduction in land surface temperature. Though these forests do use more water, whether or not that is a problem in this music part of the world probably remains an open question. Okay. We can also consider flux towers as anchors for machine learning upscaling, right? Where the goal here is to create spatially explicit maps of carbon uptake, but informed by flux tower data, let's say as opposed to soil carbon or tree biomass data. And products like these already exist, for example, Fluxcom, but those that do tend to be focused on predicting land carbon uptake globally and at scales that are coherent with Earth system model outputs. We think there's a lot of opportunity to sort of hone in our focus on specific biomes, right? Specific categories of natural climate solution management and specific regions, right? Informing these algorithms with more targeted and relevant data. We're also excited about the idea of gold standard data sets from representative ecosystems, including some managed with NCS relevant treatments and others managed more as baseline controls. We imagine these data sets could include information from flux towers, information on soil carbon and tree biomass, and a whole host of other biometric variables and remote sensing variables that can really give us a complete picture of the processes governing any changes in carbon uptake or greenhouse gas emissions. These data would, of course, be open and freely accessible, where they could be used, for example, to understand heterogeneity in the verification and monitoring protocols currently in use in the carbon market system, right? They're very variable. So consider the information that we might learn from something like a carbon market model intercomparison project. We could also use these data sets to better understand systematically the biases and what we understand about climate mitigation from tree data, right, as opposed to flux tower data. We could also use them as a functional test bed for new approaches for monitoring and verification. When we think about flux towers as a tool for monitoring individual NCS projects, right now the benefit cost ratio isn't always favorable because flux towers are expensive to install and operate. However, an analysis led largely by my colleague Stefan Metzger suggests that somewhat counterintuitively, if you increase the size of the flux tower so that you sense a greater fraction of the land surface and also add in some ancillary data streams, you can use machine learning and other approaches to create gridded flux maps at the landscape scale, right? Which actually increases substantially the benefit cost ratio of systems like this as a monitoring tool, at least for larger projects. Okay, thinking back to the problem of permanence or durability, this one remains thorny, right? Because on the one hand, carbon markets don't consider the possibility for climate feedbacks at all in their accounting. But on the other hand, our Earth system models don't do a great job on agreeing what those climate feedbacks really mean for land carbon uptake. So we need to keep hammering on this problem. We think that there are a few questions that we could address in the near term that are relatively tractable. For example, understanding if models might agree better if we're focused on the change in carbon uptake attributable to a specific NCS like reforestation, or if we hone our attention at regional as opposed to global scales. Right? When we think about durability and permanence, we also have to recognize that we are not completely naive, right? If we think about, for example, the Eastern United States, this is a part of the country that receives a lot of rain, right, where droughts are relatively infrequent and less severe compared to the Western United States. It's a part of the country where tree species richness is high, which inoculates our forests against devastating impacts of insect outbreaks. And it's also a part of the country where forests historically dominated the landscape, right? So putting these pieces together, we could probably conclude that the Eastern United States is a less risky place for a strategy like reforestation than the Western United States, and perhaps our policy needs to be designed with these sorts of factors in mind. And if you want to see a much more elegant demonstration of what I just said, please check out this work by Bill Landerig. All right, so to summarize, generally speaking, Despite substantial enthusiasm, the realizable benefits of natural or nature-based climate solutions are difficult to quantify and largely unknown. However, we have substantial opportunity to leverage decades worth of investment in tools and analytical approaches to confront this uncertainty. So I'd like to end by thanking my collaborators again and urging you to reach out to me over email if you'd like to join the AmeriFlex Working Group on Natural Climate Solutions or if you have questions. And looking forward to seeing some of you in New Orleans.